My esteemed listeners, in this tutorial we will bring about or discuss efficiency analysis of algorithms, and we will choose some benchmark algorithms. We will write the algorithms and we will arrive at their efficiency case and we will fix them asymptotic notations. Okay, this tutorial comes as a once again in sequence with its precedent tutorial, that is analysis of algorithms 2, where exactly we talked about what is efficiency analysis and what is asymptotic notations, how they are to be fixed and how they are to be understood, as to why they are to be done. Okay, all these things were discussed. Therefore, there is no gap as such this algorithm, this particular session comes as a link to the tutorial that we had in the previous session. Okay, so we will take up examples, 3 to 4 examples, and we will write the algorithm and we will analyze their efficiency. Okay, and at the end of this session some few questions are given, and my esteemed listeners will definitely venture it out and they will be definitely able to solve them, okay, after the end of this tutorial. Okay, this is algorithm biggest element, finding biggest element in an array. Okay, and this is how it is the algorithm is written. Algorithm, you need to write like this, biggest element, and I told you in the previous session that the name of the algorithm should be given in camel case representation, and the name of the array is AR, and it runs for 0 to n minus 1, n elements. Okay, what it does, the first heading is what it does, and you need to write all these. Okay, this is called as housekeeping in an algorithm, and this will remove any ambiguity about the algorithm. Okay, this needs to be done. Okay, since this is not a program, you need to explain as to what exactly this algorithm is doing. That is the first comment. What it does, it finds the biggest number in an array. What is the input? An array AR 0 to n minus 1. Okay, it is not ordered, that is very important. Okay, output, it returns the biggest element. Okay, so the strategy is assign the very first element to be the biggest element. Okay, that is being done, and this element, this big element is compared with the rest of the elements, and if this is not really big, and whatever that is big will be placed into this variable. Okay, that's how the analogy goes, that's how the logic goes. Okay, for I equal to 1 to n minus 1, we need not have to start from 0 because this is assumed to be the biggest element. Okay, 1 to n minus 1. If big is lesser than AR of I, that is the next element, that is the second element, then big will be AR of I. Okay, after the completion of the first cycle, the big will be the second element, if the second element is really bigger than the assumed element. Like this it goes at the end, when the end of the array is reached, what exactly the for loop throws out is, what exactly this for loop doles out is the real biggest element, okay, that is over here. Otherwise, if our assumption is correct, then this thing only will, this element will only remain as the biggest element. Anyway, the algorithm will take care. Anyway, be sure that this algorithm really works and it will get you the biggest of all the elements. Okay, now we will analyze its complexity. Okay, we can analyze this under the framework of analysis of algorithms simply because this algorithm is non-recursive in nature. Okay, this algorithm is non-recursive in nature. Therefore, first of all, you have to define the input size. Okay, the input size is the number of elements. Okay, the number of elements, that is n, the size of the array. Okay, the basic operation is exactly comparison. Okay, the basic operation that is, okay, that works really, that consumes most of the time is the comparison that happens. Okay, because the algorithm has to compare, okay, whether the next element is bigger or not. Okay, if it is bigger, then only assignment will happen, or we may be confused why this is not a basic operation. Okay, this basic operation happens if and only if the big is lesser than AR of I. However, the algorithm should check all the elements. It should compare all the elements with this big. Therefore, this is the basic operation. Okay, this consumes most of the algorithm time. Basic operation. Therefore, we will take comparison as the basic operation, and we will develop a function which is equivalent to running time of the algorithm. Count of number of times basic operation is executed, that is comparison is executed, is given by let us go back, and it is there within this for loop. This for loop runs for 1 to n minus 1. This for loop runs for 1 to n minus 1. Therefore, we will write like this. Okay, I equal to 1 to n minus 1. There is only one comparison that is available in the for loop. Therefore, we need to get an expression for this. Okay, how many times the basic operation is getting executed. Okay, the meaning of this sigma is, as you know, okay, our fundamental understanding about this sigma tells that 1 is to be added up to, starting from 1 up to n minus 1 times. Okay, and we will take an analogy over here. We will take a simple example. If it is something like this, it is I equal to 1 to 5. If at all it were to be like this, the meaning is starting from 1 up to 5, you add 1. So the answer should be 5. You cannot do this if the number happens to be very big over here. It is excruciating, and it calls for a drudgery. Therefore, what we can do is simply it is upper limit minus lower limit. Okay, this will give you 4, but the answer is 5 exactly, because it is to be added 5 times. Therefore, 5 minus 1, upper limit minus lower limit plus 1. Okay, so this 1 will get cancelled, and we will be left with 5, which is the correct answer. Therefore, we will do like this. With the same analogy, we will bring in over here. Same technique we will bring in over here. So upper limit is n minus 1. Okay, lower limit is 1 minus 1, n minus 1 minus 1 plus 1. Okay, this one and this one will get cancelled, and we will be left with n minus 1. Therefore, CFN, the time consumed by the algorithm in terms of basic step executing the comparison as a basic step executing n number of times, okay, that is a certain amount of time, okay, repeatedly, is equal to n minus 1. Therefore, the higher order term here is n. Therefore, this belongs to big theta of n. Okay, higher order term, directly we can place it, and we will never venture into analyzing this into big O or big omega, because customarily the worst case analysis of every algorithm is given the asymptotic notation to be in theta. Okay, because theta fixes both upper limit, both upper bound and lower bound for the algorithm. Therefore, it is big theta n. Now, had you been a question asking you to fix this algorithm to upper bound, that is O, big O, then we would have said it belongs to big O of n log n, because next higher order of growth is, or higher efficiency case is n log n. The omega is log n. Okay, big omega of log n, or big O of n log n, and big theta of n. Okay, so that's how it goes. We will go to next algorithm. Okay, that is being done over here. Okay, I just explained you by writing. Okay, now we will take up the second example to check the element uniqueness in an unsorted array. Okay, to verify, this algorithm verifies whether all the elements in the array are unique. They are different, they are discrete, and they are different. Okay, to do this, let us discuss the logic first. Okay, let the elements be 2, 5, 7. Okay, 7, 6, 1. Let us say, and every element is to be compared with the other element so that uniqueness is maintained. If any comparison brings out same valued elements, then it is not unique. That is the strategy. For this, we will write it down once again. Okay, we will write the array elements once again. 2, 5, 7, 6, 1. Okay, this 2 is to be compared with 5. It should be compared with 7. It should be compared with 6, and it should be compared with 1. There is no fun in comparing 2 with 2. And as far as 5 is concerned, 5 is to be compared with this 7, and 5 is to be compared with this 6 and 1. Okay, it should not be compared with 5 again. There is no fun. Once again, 7 should be compared with 6 and 1. 6 should be compared with 1. So 1 will be left unattended. In the melee, 1 will also have been compared with the other elements. Therefore, this algorithm needs 2 for loops. the first for loop, outer for loop, will let each and every element go for comparison. It will let each and every element to go for comparison. In doing so, it is essential that the outer for loop will send the first element and this element, first to last minus 1. Okay, there is no need to go up to the last element because it will have been compared. Okay, it will have been compared with the rest of the elements by the time the control reaches this particular point. Okay, therefore outer for loop is meant for letting the elements for comparison, and inner for loop does comparison. Okay, that's how it goes. Therefore the outer for loop, okay, it will let the elements for I equal to 0 to n minus 2, because 2, it is 2, it is not less than, we are not using any symbol, 2 up to n minus 2. This is n minus second, n minus 2, 2th element. Do for j equal to, this is for comparison. So while comparing, it should start from here, the next element. Therefore next element is I plus 1. I plus 1 to n minus 1. It should go up to the end because last element should not be omitted while comparing. Therefore I plus 1 to n minus 1 do. If fi, the element that is let out by the outer for loop at any point of time equals to fj, okay, which the inner for loop is bringing, then the algorithm will immediately return 0. Okay, after the happening of both the for loops, okay, every element will have been compared with the rest, okay, and the comparison will be over, and nowhere in between it has sent 0. Therefore it will return 1, stating that the array contains all unique elements. Okay, now we will try to analyze the algorithm. Okay, so it has two for loops. Okay, the inner for loop runs between I plus 1 to n minus 1, while the outer for loop runs between 0 to n minus 2. Okay, and the comparison is the basic operation. Okay, we will go for this and we will write, therefore number of comparisons, okay, count of number of comparisons as the function of input size equal to the there is only one comparison that is happening between I plus 1 to n minus 1. Okay, I plus 1 to n minus 1. So I plus 1, okay, I plus 1 to n minus 1. Okay, while this is happening between, okay, I equal to 0 to n minus 2. This is happening like this. Therefore we will expand the inner, okay, inner summation symbol. So I equal to 0 to n minus 2, let it remain as it is. This is upper limit is n minus 1 minus of I plus 1, it is minus I minus 1, okay, plus 1, okay, plus 1 I told you earlier. So plus 1 minus 1 will cancel. What we are left with is n minus 1 minus I. So we will just group the constant terms and we will leave the variable term aloof, okay, n minus 2. Here the constant term is n minus 1, okay, and the variable term is I. Therefore I will put a different sigma over here because the dealing with a variable under the ambit of sigma is something different from dealing with a constant under the ambit of sigma. Therefore it is I. Okay, I will write it over here. So this can be simply n minus 1 into n minus 2 minus 0 plus 1. So n minus 2 plus 1 minus 0 plus 1. Okay, then minus, this is nothing but the series. Okay, you go on substituting value for I, 0 plus 1 plus 2 plus 3 up to n minus 2. So this will generate a series something like this, 0 plus 1 plus 2 plus 3 etc plus n minus 2, n minus 2. If the series runs up to n, so it is arithmetic series. The summation of the series is given by n into n plus 1 by 2. This formula you know. Okay, you have studied this in maybe in middle school level. Therefore in place of n, but this series ends at n minus 2. Therefore in place of n we will substitute n minus 2. So n minus 2 into n minus 2 plus 1. N minus 2 plus 1 is nothing but n minus 1 divided by 2. Divided by 2 is there. Okay, right. we will just erase this and we will simplify that. Okay, we will make a place over here and we will do that anyway. Right. Okay, now we will start doing, okay, continuing wherever we have left. So this is n minus 1 into n minus 1, okay, the first term, n minus 1 into n minus 1. Okay, the second term is minus of n minus 1 into n minus 2 divided by 2. If you take n minus 1 as the common factor, what we left with is, and 2 as LCM, we will get, okay, 2n minus 2 over here for this particular expression, and minus n minus 2 will remain over there because n minus 1 is taken as a common factor, so it becomes plus n plus 2. 2 will get cancelled, and 2n minus 2n plus n, okay, 2n minus n, this is actually minus n, okay, sorry, 2n minus n, it is n. So what we get here is, okay, what we get now is, we will just go about it, okay, right, okay, n minus 1 into n divided by 2. Okay, if you expand this, you will get n square by 2 minus n by 2. Here higher order term is n square by 2, this is actually n square by 2, okay, or half into n square minus half into n. Okay, multiplicative terms can be ignored because they will cancel away when you try to find the order of growth. Therefore, this algorithm belongs to the complexity of, okay, C of n belongs to the complexity of big theta of n square. Yeah, we will go to the next algorithm. Yeah, matrix multiplication. This is a well-known algorithm, known to all of us, but anyway, for the sake of completeness, we will do this, okay, because this involves in a cubic complexity. We will see that later, okay, very quickly we will see that. Okay, anyway, you know, when two matrices are multiplied, one is n cross n, the other one is also n cross n. Okay, there is a question of compatibility, but anyway, since we are considering square matrices, compatibility will never arise. Okay, otherwise, to recall your memory, if this is m into n, if the other one is p into q, n should be equal to p. For the compatibility in multiplication, and the resultant matrix will have m into q. Okay, here since we are involving with a square matrix, because multiplication of two square matrices involves too many multiplications when compared to two rectangular matrices. Okay, so if this is the example, okay, let us take a very simple example of 2 by 2 matrix. This is 1, 2, 3, 4, and this is, let us say, 2, 2, 1, 1. When you multiply, the first row will be getting multiplied by the first column, okay, and the first row is once again multiplied by the second column, and the way in which the elements are generated is something like this. You know this anyway. For the sake of completeness, I am just telling you, recalling your memory, okay, don't think otherwise. 1 into 2 plus 2 into 1. So this is one element. The other element is once again 1 into 2 plus 2 into 2. Yeah, 1 into 2 plus 2 into 1 once again. Okay, like this we're going to generate. So now we need a mechanism to generate the columns for the matrix, resultant matrix, to generate the row, generate the column, generate the row, and generate the elements by themselves. Okay, how to generate the elements? Elements are generated by multiplication and addition. Okay, multiplication and addition. So for every element should be generated anew. Every element should be generated afresh. Okay, therefore this is the three mechanisms are involved. Okay, in matrix multiplication we have to remember three mechanisms are involved: to generate columns, to generate rows, and to generate elements themselves. Therefore this is the algorithm. Output returns C, A cross B, A into B. For I equal to 0 to n minus 1, okay, do For j equal to 0 to n, this is to generate columns, this is to generate rows, this is to generate elements. Okay, to begin with, I told you every element is afresh, therefore it should have an accumulator before we enter into the third loop, where exactly multiplication and addition will happen simultaneously. Okay, C of ij equal to 0, therefore for k equal to 0 to n minus n, C of ij equal to earlier value of C of ij plus a into a of ik into b of kj. Okay, this is the multiplication formula. And here when you start investigating about the base, okay, the basic program, basic operation, here there are two operations are happening. One is assignment, other one is addition, and other one is multiplication. Among all the three operations, multiplication will consume most of the time, therefore multiplication is taken as the basic step. Okay, therefore we will just formulate this into some kind of a formulation. We will bring some kind of a formality. So here multiplications is the basic step, therefore number of multiplication that happens as a function of order of matrices equal to sigma, the innermost for loop, okay, which runs from 0 to n minus 1, k equal to 0 to n minus 1, and here comes 1 multiplication. And once again this is repeated by 0 to n minus 1 again, and these two repetitions are repeated yet again, 0 to n minus 2, n minus 1, sorry, n minus 1, n minus 1, n minus 1. And if you expand this, you will soon find n cube directly coming, because here n minus 1 minus 0 plus 1, n. And once you introduce this one, this will also give you n into n, and this will also give you n into n into n cube. Okay, n cube is the final outcome. Okay, n cube is the number of times the multiplication happens. Therefore matrix multiplication belongs to big theta of n cube. It is cubic efficiency case or cubic complexity. Right, we will end up with this. Okay, this is a peculiar example. Now you have to sum the series. The series is also special. First term is 1, second term is 1 plus 2, third term is 1 plus 2 plus 3, fourth term is like this, and it goes on adding like this. It is okay, elements are generated here in this series by addition once again. Okay, the input is this, how many terms you want to generate. If the number of terms equal to 4, if the number of terms equal to 3, the answer should be 1 plus 3, 1 plus 3 4, 4 plus 1 5, 5 plus 2 7, 7 plus 3 equal to 10. Okay, this is summation of summation. Let us say summation of summation. Sum series. Okay, the input is how many terms, number of terms. What it does, sums up a series. Input number of terms n, output the value of sum. Okay, sum is equal to 0. Okay, this one, individual sums equal to 0. Big sum, this and this equal to 0. Okay, you assign two variables. These two are accumulators anyway. Two accumulators are there. For I equal to 0 to n, do sum equal to sum plus I. Okay, it should be sum plus I. This is I actually. Okay, sum plus I. Big sum is equal to big sum plus sum. Big sum is gotten over here, that means these steps, and it will be added. Big sum means here till here, big sum is still here. Okay, this is sum. In every iteration this is sum. This is sum 1, sum 2, sum 3, something like this. Okay, this will be sure that this will give you correct answer, but anyway. Okay, anyway, we will go about analyzing this. And there are two basic steps over here. This basic step consumes most of the time because it has to involve adding this sum again. Okay, so this comes as a double addition, exactly speaking, because the sum is obtained from the first step. Therefore we can take the addition to be basic step. Okay, it happens at only one place, let us assume. Even if you take consume it as 2, subsume it as 2, there is no problem. Number of terms, as the input says. Okay, sigma. Okay, you can take there are two basic operations anyway, no problem. Okay, I equal to 0 to n. So it is 2, you take common factor out, and you put it over here. 1, I equal to 0 to n. Okay, it will get you 2n. n minus 0 plus 1, n, 2n. So here when we attach this to efficiency case, we need to ignore the multiplicative coefficients, because multiplicative coefficients will cancel away when we try to find order of growth. You know that. Okay, therefore this belongs to big theta of n. Okay, big theta of n. So with this we will see, there are some examples given to you. Please try them out. Okay, these are all typical problems that may arise in academic circles and also in problem solving circles. Okay, therefore at this point I am going to end up this tutorial. Okay, bye.